calculate moles, determine if there's a limiting reactant or not. And then if there is, make sure that you use the limiting reactant to calculate the amount of methanol that you would expect to be produced. You wouldn't. It's just part of the problem. I tells you that. Yeah. Let me know if you're stuck, if I can help you. All right. You gotta set up a location. So you gotta kind of like figure it out based on what it says. Methanol manufactured by a combination of carbon dioxide. That's the so Did you get an equation, something like that? All right, good. All right, did anybody get the number of moles in CO? Yet?
2,446.
2,446 moles. That's a pretty big number, as we would expect, because this is in kilograms. So one way that you can do these types of problems, if you want, and if this messes you up, don't just ignore what I'm about to say. But you can do this in terms of kilomoles instead of just moles. And that way you don't have to do any conversions between kilograms and grams to get to moles. So like those numbers are grams per mole, but they're also kilograms per kilomole or milligrams per millimole. So if you keep everything constant, as long as you keep the same prefix, whether it's kilo or milli or whatever, kilo or milli or whatever, you can keep that all the same. So if you didn't want to do that conversion, you could just report this as 2.45 kmol. If you multiplied that, or you divide that 68.5 by 12 plus 16 is 28, you get 2.45. And then you don't have to do that additional step of converting to grams first. But that's up to you. All right, so then that's 2.45 kmol. And then for hydrogen, hydrogen is 2, right? 1 for each, so it's 2. So that's 8.6 divided by, 8.6 divided by 2. Try that again, 8.6 divided by 2, 4.3. Kilomoles. All right, so now we have to think about a limiting reactant. Now that we've got those two things in moles, what's the limiting reactant? CO. No, I think it's hydrogen. Let's check it and see. Am I wrong? Maybe I'm wrong. That's how we can do the calculation. So we can say 2.45 kilomole of CO. And then we want to figure out how many kilomoles of CO are needed, or how many kilomoles of hydrogen are needed per mole of CO. So the equation tells us that we need 2 of these for every one of these. And so that is 4.90 kilomoles of H2. So that tells us that we need more hydrogen than we actually have. Right? We need 4.90 kilomoles. We have 4.30. So that makes hydrogen the limiting reactant. You see how that goes? We could also do that the other way. We could have started with, there's no need to do both of these, but just for instructional purposes, we could also go the other way and say for the 4.30 kilomoles of H2 that we need, we'd need 1 of these per 2 of these. So that would give us 2.15 kilomoles CO. And you can see that we have more CO than we need. So there's an excess of CO. So hydrogen is our limiting reactant there. Those calculations tell us H2 is limiting and CO has 0.30 kilomoles excess. All right, so now we can use that number for the limiting reactant and solve for our theoretical yields. How would you do that? Anybody try it?
You can find out how many grams or kilograms or whatever are in the amount of moles you get with the limiting reactant.
Right. So we'd hold on. So we have to look first at the molar ratio. In this case, it's 1-to-1 because 1 molecule of CO makes 1 molecule of methanol. So we don't need to multiply by anything. We can just say that the 2.45 kilomoles of CO also means, based on the reaction we see above. Whoops, sorry, going the wrong way. Let's fix that. The 4.30 kilomoles of hydrogen leads to 4.30 kilomoles of methanol, because that's wrong. Sorry. My eraser's broken now too. We're just freaking this whole thing out. Probably can't. All right, so I can turn it different colors, but I cannot erase it. Okay, we'll just pretend it doesn't erase. Oh, okay. Does that work if I do this? Oh yeah, it does. Can like erase things by scribbling on it enough times. It's kind of fun. Except sometimes it doesn't work. So, all right, let's go through and do this then to find. Let's do it all the way out then to find the amount of methanol that we expect to produce. So we have to start from the quantity of hydrogen because we decided that was the limiting reactant, right? All right, let's try that. 4.30 kilomoles of hydrogen. And the stoichiometry tells us that these should be 1 to 2. The little arrow doesn't show up anymore either. Restart this a minute, because this is kind of annoying. Okay. Let's just hope that that saved it. We'll see. Sure, it'll restore it. All right, it's all still there. Good. All right, so the equation here tells us that we've got 1 of these for every 2 of these. And that's where these numbers come from. Yeah, I have an eraser now too. Okay, good. So then our last step is going to be finding the mass of the methanol. We can just keep that in this same line. We want to know, we want to get rid of these kilomoles of methanol and instead have kilograms of methanol. So CH3OH, that's 12 plus 3 is 15, plus 16 is 31, plus 1 is 32. Is that right? Is that what you got? Okay. All right, so we're going to go 4.30 divided by 2 times 32 should be 68.8 kilograms of methanol. And that's what we call the theoretical yield, how much we would expect to get based on every single molecule transforming, which we know that's not actually going to happen, but that's how we plan our synthesis. But now the rest of the problem says, if this is how much is actually produced, what is the percent yield of methanol? So if instead of 68.8 kilograms, we actually make, what was that, 35.7 kilograms, what is the percent yield? Percent yield is the actual over the theoretical times 100%. So in this case, that's going to be 35.7 kilograms divided by 68.8 kilograms. Which is 51.9% yield. So it's about 50% yield. All right, about half as good as we might like. Is this yours? No? Okay, I was just sitting on the desk.
Yeah, no, I put it up on the desk. It was on one of the tables the other day.
Oh, okay.
Yeah.
I thought I sat over here. Okay, I'll put it back in our last phone. Okay, so you think you could do that? I think you can do it. I think it takes practice. So like I said, we'll have a quiz on this on Tuesday. So make sure that you get plenty of practice with this over the weekend as you go through the homework. Okay, let's go on, and we're not really going to change anything, but we're going to look at a different way to find moles rather than just weighing things out, and that's when things are in solution. When something is in solution, what does that mean? What does it mean when we have aqueous copper sulfate instead of solid copper sulfate? We talked about this before. This would be on the exam. What does it mean for something to be in solution?
Dissolved in water.
Dissolved in water. And what is happening at the molecular level when something is dissolved in water? Its ions have separated and they've been surrounded by the solvent molecules. So the way that we express that is a measurement called concentration. You've probably heard of concentration before. We've used it a little bit in lab. And the main concentration that we're going to use in this class, at least right now, is called molarity. Have you heard about molarity before? Some people kind of previous chemistry classes. Molarity is a way to figure out how many moles of solute, the stuff you're dissolving in there, are in a particular volume of water or a particular volume of solutions. The actual definition is molarity is moles of solute per volume of solution in liters. Big M. Moles of solute, liters of solution. Let's talk about how we make that before we do the calculations, unless I have. Okay. The sort of unusual thing about molarity that we don't think about all the time is notice in the denominator, it's liters of solution. It's not liters of salt. So that doesn't mean you take 2 moles of copper sulfate and you put it in a liter of water. That means you take 2 moles of copper sulfate and then you fill the entire solution so that the final volume is 1 liter. Because the solute has volume too. It's not just the solvent. I mean, if you take a few scoops of some solid, it takes up space. So it's still going to take up space in solution. Really less space, but still take up space. So the proper way to make a solution, and we'll be doing this in lab for sure, is you use something called a volumetric flask. Have you used a volumetric flask before? You know what that looks like? What's a volumetric flask look like? Kind of like draw it in the air. No? kind of like, oh, here, let me just draw it on the screen here. There's a really skinny long neck and then kind of a little bulb at the bottom. And it just has one line on it, a circle that goes around at one point on that neck of the flask. The point of that is you can measure volume very precisely, but only one particular volume. So like a volumetric pipette only measures that one volume, but does it really well. A volumetric flask only measures one volume, but does it really well. So you'd take like a 25 milliliter volumetric flask. You'd put a little bit of water in the bottom to start with. Then you dump in the solute, spray off the whey boat or whatever to make sure every little bit of it got back in there, and then dissolve it up and then fill with water until it gets just to that line. And you have to be really careful with it. You have to go drop by drop at the end, because if it goes over that line, even by just a tiny bit, you have to throw the whole thing out and start again. You can't just take some water out because the water is already mixed with some of the solute when it's in there. So you just like fill it up, and then when you get to the top, you could go drop by drop until it's right at that line. So we end up with being able to do things like this: calculate the molarity of a solution prepared by dissolving 11.5 grams of solid NaOH in enough water to make 1.5 liters of solution. So all you got to do for that is convert grams to moles, and then put it over the volume, and that's your molarity. 11.5 grams NaOH. And we want to get rid of grams and have moles. So that's Na is 23, O is 16, that's 39, and H makes 40. So that tells us we got 0.288 moles. .288 moles solute in 1.50 liters of solution. Gives us 0.192 molar. So that tells us that there would be 0.192 moles in 1 liter of that solution. See how that works? Maybe? Yes? No? Okay. The power of this, or the kind of the point of this, is that we can, we'll skip some of these types of calculations. We can figure out the number of moles of something in a solution. So when we have a reaction, we can know the number of moles. Like in our previous reaction problems, you had to be given a mass. It had to say like, okay, you've got 8 grams of this, and then you convert it to moles, and then you do all the other stuff. But when we're working with solutions, we can't really weigh them because most of that weight is just water. So instead, we have to know the concentration. Then we calculate by volume. Then we can figure out the actual number of moles. So like, look at this example. Calculate the number of moles of chloride ions in 1.75 liters of 1 times 10 to the minus 3 molar, that's the concentration of molar, zinc chloride. So the molarity here, this 1.0 times 10 to the minus 3 molar, that's expressed in terms of zinc chloride as a whole, like as a whole thing. So that looks like, what that means is 1.0 times 10 to the minus 3 moles of zinc chloride per 1 liter of solution. So that much zinc chloride per 1 liter of solution. But the question is asking for number of moles of chloride ions. And we're saying 1.75 liters of the solution. So we have to kind of set this up again as almost like a conversion type, vector label type problem. And it looks like this. 1.0 times 10 to the minus 3 molar means this. So we start with that. first, we just multiply by the actual volume that we have. So 1.75 liters of solution. And that's going to give us, that's going to let those cancel. And that's going to give us the number of moles of zinc chloride as a whole. But as you said earlier, when zinc chloride is in solution, it actually breaks apart. So one zinc chloride unit breaks apart and becomes a zinc ion and 2 chloride ions. See how that would work, right? Zinc and then 2 chlorides. So we have to account for that in what the question is asking, because we really care about the concentration of chloride ions, not zinc chloride as a whole. So the concentration of chloride ions, we need to know that there are 2 moles of chloride ions per each 1 mole of zinc chloride, each formula unit, because it breaks apart in solution. And the little 2 here tells us there's 2 chloride ions per formula unit. So you got to make sure to multiply that by 2 to get it to all work out. So 1.75 times 2 is 3.5, right? Yeah, 3.5. And 3.5 times 1 times 10 to the minus 3 is 3.5 times 10 to the minus 3. Make sure I did that right. So that can tell us exactly how much chloride we have. And the power of that then is when we do a reaction in the lab and we want to use something that's in solution, we know how much we're using based on volume. So we can measure out a volume and know exactly how much solute is in there as long as we have the concentration also. Okay. Let's see, how far can we go with this? Sorry, I hit home. So let's look at solution, and then we will, that's pretty much all you need to know, and then we'll go back to if you have any questions about exam stuff. So the other part of solution chemistry that we need is to be able to make dilutions. And this is important in chemistry labs, is really important if you go into something like pharmacy or other types of medical fields where you might be preparing these kinds of solutions. It just means you have a solution of a certain concentration, you add water, that concentration goes down. So how do you know how much water to add to get to the new concentration that you want? And the key to dilution problems is recognizing this. You're not changing the amount of solute when you do a dilution. However much solute was in the original solution, all you're doing is pouring water in it. You still have the same amount of solute, you just change the volume. So the moles stay the same, the volume changes, and therefore the concentration changes. And there's we're going to do this example kind of full out moles to moles, but then I'll show you the shortcut. And those of you who are around, who stuck around, and I think, was it yesterday when we did that a little bit in class at the end. So yeah, what you can do for these is just figure out the number of moles and then figure out how much volume you'd need to get to a particular stock solution or to get to a particular concentration. So in this case, we need 500 milliliters of 1 molar acetic acid. All right, so how many moles is that? If it's 1 molar, that's 1.00 moles acetic acid. I'm going to use a different abbreviation for acetic acid, ACOH. It's kind of the organic chemistry abbreviation. But that molarity tells us that there are 1.00 moles per 1 liter. Since we have 0.5 liters, that tells us that in the final solution, we want 0.500 moles of acetic acid. If we want half a liter of a 1 molar solution, that means we need half a mole. See how that works? Okay. So the second part of the dilution then is how much of the stock solution do we need to take to get that half a mole? And the stock solution has a different concentration. The stock solution is 17.4 moles per liter. So we're saying, in this case, 0.500, well, no, let's put that in. That was clear. 17.4 moles per liter times how many liters gives us 0.500 moles. We want half a mole. We have 17.4 moles per liter. So how much of that do we take out to get exactly that half a mole? In this case, you just then divide 0.5 by 17.4 to solve for that unknown. And that tells us that we need 0.0287 liters, or 2.87 milliliters. So to make this 500 milliliters of a 1 molar solution, you would take 2.87 milliliters of the stock solution, exactly, and then you would dilute that to 500 milliliters, to half a liter in a volumetric flask, and then you'd have your final solution that had the appropriate concentration that you wanted. Glassware that you do that with, oh, we did talk about volumetric flask. Of course, you know the volumetric pipette that we've already going to work with, this guy. Another type of pipette that we haven't worked with is called a graduated pipette. That one is actually straight and then has graduations on it so that you can measure exactly that amount. So we would use that measuring graduated pipette for that 2.87 milliliters, because you would move the liquid level. Let's say you'd start at like 1, and then you'd go down to 3.8 or whatever. No, they're done in the opposite way. So you could go up to like 2.87 and then let the liquid level go down to 0, and then you'd have exactly your 2.87 milliliters. And then you'd use that volumetric flask to fill it up to the rest of the amount. The graduated pipettes are the ones that you use with those rolly pipette top things. You know what I'm talking about? That's not a great way to describe it, though. I think ours are green or red, and you like pull the little wheel and it goes up and down. Those, as you notice, were a little bit more frustrating to use with the volumetric pipettes, but they work really nicely for these when you can carefully control your level and you're not trying to just let it run out with gravity. All right. So then here's the shortcut that everybody remembers. You can always do it this way. As long as you remember that the moles stay the same, you can solve for how many moles you need and then figure out how much of the stock solution you need to take to get that many moles. But the shortcut that everybody thinks about is this. Another way of saying that the moles stay the same is the concentration times the volume when you start is the same as the concentration times the volume when you end. And that's because concentration is moles per liter, volume is in liters, so concentration times volume equals moles. Concentration times volume is moles. Concentration times volume is moles. So we're doing the same thing. We're saying moles have to stay the same. When we change the volume, we have to change the concentration. So in this case, same basic question as what we just did. What volume of 16 molar sulfuric acid must be used to prepare 1.5 liters of a 0.1 molar sulfuric acid solution? So what you start with is the stock solution. So that's that 16 molar from the stock solution. And this is that unknown volume that we had before. On the other side is what you want, the volume you want and the concentration you want. So you want a 0.1 molar solution, you want 1.5 liters of it. So then you just solve for V1. 0.10 molar times 1.5 liters divided by 16 molar. It's 9.38 milliliters or 9.4 milliliters. So you need 9.4 milliliters of your stock solution. You would dilute it to 1.5 liters, and now you have a 0.1 molar solution. We'll be doing that in the, well, in a few labs, actually, because we'll need to make some different dilutions to measure some different concentrations. So that'll be coming up in the next couple weeks. All right. This is basically a sum up of what we've done. You should be able to do this, practice these types of problems. There's a million of them in chapter 4. Don't just focus on the mastering chemistry. Make sure you also go to the book and do those problems. But basic idea, as we did at the beginning of class today, you write you figure out what's happening, what kind of reaction is going to occur, then you write a balanced equation. And this is specific for precipitation reactions, but if you kind of take out some of these net ionic stuff, it's true for any kind of reaction. You write your balanced equation, you calculate your moles, you figure out what's the limiting reactant, calculate moles of product or products or one of the reactants or whatever is actually required by the problem, and then convert to grams. So, hopefully you can get used to doing those types of problems. We'll be doing them a bunch, and it's always the same. So once you kind of get how to do these problems, you should be set every time one comes up. Nothing really changes in terms of those types of things. So let's do one example here. The second one here, where we're now dealing with concentrations instead of masses. Actually, both. Actually, concentrations and masses. So when aqueous solutions of sodium sulfate and lead nitrate are mixed, lead sulfate precipitates. Calculate the mass of lead sulfate formed when 1.25 liters of a 0.05 molar lead nitrate and 2.0 liters of 0.025 molar sodium sulfate are mixed. Right, so you're given reactants, you're given quantities. We got to put together the reaction, figure out if there's a limiting reactant, and then solve for the mass of product. So see if you can do that. Write a balanced equation, solve for the moles of each based on their volumes and concentrations, and then figure out how many moles and ultimately how much mass of lead sulfate is formed. So we'll do it just like we did at the beginning. Go ahead and get started, see what you can do, and I'll kind of join in a little bit. The other kind of wrinkle you could put in here would be to not give you the formulas. That would be a common way to ask this question. That they would just say the words sodium sulfate and lead nitrate, and you'd have to write it down from there. You get an equation something like that, and then I just wrote the solution quantities. So how do we get moles from those solution quantities? You just multiply them together. So molarity, molar is moles per liter. So you multiply that by liters, and you got moles. So that's comparing those two then, what's the limiting reactant?
Sodium sulfate.
Yeah, sodium sulfate, because the equation tells us it has to be 1-to-1 in moles. We've got 0.05 moles of sodium sulfate, 0.0625 moles of lead nitrate, so we've got extra lead nitrate, 0.0125 extra lead nitrate. The stoichiometry also tells us that 0.5 moles of this has to make, or 0.05 moles of this has to make 0.05 moles of that, because that's 1-to-1 according to the reaction, right? 1-to-1. So then we can answer the last bit, which is this many moles of lead sulfate times the molar mass Did anybody get the molar mass of lead sulfate? Thanks. So 0.05 times 303.2 is 15.2 grams lead sulfate, which is what we're asked for. So that's how much precipitate forms when those solutions are mixed. Same idea. The only difference here is we're starting with solutions instead of individual masses of reactants. All right, well, happy practicing. No, one thing I should note here, I did not talk about acid-base reactions and titrations and things. We're going to do titrations in lab, and we'll get into the whole mechanics of it then. To solve acid-base titrations, I want you to think about them not as anything different. So look at this. Look at this one. This is how acid-base titrations usually how they go. You're taking an acid and you're putting it into a base, or you're taking a base and putting it into an acid, and you want to know how much you need of one to completely neutralize the other. So it's really just a stoichiometry problem. Take your balanced equation of HCl plus NaOH yields H2O plus NaCl, or whatever the acid and base are, and then figure out how many moles of one you have and how many moles of the other one you need. And that's it. So you usually have some unknown concentration and a known concentration. But it's not a different kind of problem. It's exactly what we just did. Exactly what we just did here. If one of these, rather than looking for a limiting reactant, if one of these were unknown, we'd have to figure that out from the other one. And we could do that. So go ahead and do some practice problems with that. If you have trouble with it, certainly let me know and we'll talk about it. But don't think of it as this separate kind of problem that has its own special techniques and equations. It's just another reaction problem, but your reactants are an acid and a base instead of two ionic compounds. So that's it. All right, we got about 20 minutes left. So what do you want to talk about? Do you have questions or things that have come up that you're concerned about for the exam tomorrow? Homework things. Did you forget your glasses? Did you forget your glasses? Yes, that's good to me. Yeah. All right. It's online, so you can check it later. You can see it.
Is this the part one, the first part go blank? Or
Yeah. About half and half.
Okay.
Should we do that really annoying kind of multiple choice where every question has like E, none of the above, like none of these are correct? Have you ever done that? And then you never know because you like don't know if your answer is wrong or if it just isn't a choice. No, okay, we won't do that. Nothing? Stare at each other? You don't have to stay, I mean, but I just wanted to leave a little time in case you had some questions before tomorrow. Oh, sorry, one thing before you go. We will not have calculators in the room tomorrow, so make sure that you bring some. I might be able to rustle up a couple if you forget, or if you tell me today that you know you're going to need a calculator tomorrow, I can definitely get you one, but please bring your calculators. You can't use your phones.
Your YouTube channel.
What?
Your YouTube channel has all that on there as well?
Yeah.
Nice.
It's linked on Blackboard. I don't know how you find it. I'm looking for it. You have it for my name, probably. But it's like the combined works is the class.
Can you go over an oxidation?
Yeah. Let's pull one from the book because that's usually where I grab stuff. I got the wrong book though, of course. Okay. All right, so let's take a look at these. Yes. Right. Determine whether or not each reaction is a redox reaction. For all redox reactions, we did this, didn't we? We did one similar. Anyway, so to figure this out, you need to first notice if there's a change in oxidation state. Easy ways to find that. Of course, you can always go through and find the oxidation state of every element in every reaction, and we'll do that a little bit here to practice that. But the easy ways to look for it is first look for things that are in their elemental state. Like in this case, we've got lithium and chlorine, and then they become a compound. So you know they have to change oxidation state. Because if they started as this in this elemental state and then they become a compound, there had to be a change there. So other things is just obvious changes of charge, like Al goes to Al3+. Again, you can notice that this is an element and then it becomes an ion. That's clearly that difference. And then again in carbon. So actually in most of these you see that if we start with an individual element, that's usually a good sign that it's an oxidation reduction type reaction. The way you can tell, or the way you would go with C here, so let's look at C because that one could be trickier. We see these things kind of mixing together, and it would be pretty cumbersome to go through and calculate the oxidation state for every element in every part of that reaction. So how can we know relatively quickly and easily that whether or not this one is a redox reaction? Any ideas? How would you go about this? Well, here, I'll give you some tips then. One thing you want to always look for, and this is true for any kind of reaction, but especially in this case, look at what changes and what stays the same in the course of this reaction. For instance, we see the nitrate ion, NO3. Everybody see that? There's nitrate ion at the beginning, there's nitrate ion at the end. So that tells us there can't be any oxidation or reduction. If that had gone from a nitrate ion to a nitrite ion, like NO3 to NO2, that would be perhaps oxidation. Actually, that would be reduction. But in this case, nothing changes, so we know that stays the same. Then we can look at the charges of the other parts, because those might be a little bit simpler. So what would be the charge on lead here? 2+, because we got 2 1- nitrates. And then the charge on lead on this side? Still 2+, so it doesn't change. Lithium, 1+ to 1+. Chloride, -1 to -1. So the tricky part of looking at the nitrogen and oxygen, we didn't even really have to deal with, because nothing else changes any oxidation states. Now let's look at answering that second question, identifying the oxidizing and reducing agents. So for A, how would you identify the oxidizing and reducing agent? Do we have a good trick that you use for that, or a technique? What's the rule about oxidizing? What's an oxidizing agent versus a reducing agent? Has to do with electrons. You remember?
Uses are gain.
Yeah, so which one's which? Do you remember?
Oxidize or gain electron? No, yeah.
Yeah.
Gain electrons and reducing electrons.
Yeah, the oxidizing agent takes the electrons. The reducing agent gives the electrons. But don't get confused, because the thing that is oxidized is not the oxidizing agent, that's the reducing agent. It's the opposite. So let's look at what's oxidized and what's reduced. And then to do this, we do need to get the individual charges. So lithium in this case goes from Li0, because it's just by itself as an element, to what in the product? Yeah, Li plus. And chlorine goes from Cl0 to Cl minus. So which one is loss of electrons? The lithium has lost in electrons, and the chlorine has gained. So that means the lithium is oxidized and the chlorine gets reduced. But that's not what we're asking for. We're asking for the agents. So that means that this one is the oxidizing agent. It takes the electrons, and this is the reducing agent, which gives up its electrons. All right, what about the bottom one, D? See if you can figure it out on your own. What's the oxidizing agent? What's the reducing agent?
See the reduce. The reduce.
Yeah. So we can do the same thing here. Carbon goes from 0 to +4 in CO2. And oxygen goes from 0 in O2 to oxide 2- in carbon dioxide. So carbon has lost electrons, oxygen has gained electrons. Another way you can think about this if you get confused in these kinds of reactions, the word oxidizing comes from oxygen because things tend to get oxidized in the presence of oxygen. So elemental oxygen, O2, is always an oxidizing agent. And if you kind of keep that in your head, because oxygen, oxidizing, oxidizer, if you keep that in your head, you can think about, well, what does oxygen do? Elemental oxygen goes from 0 to 2-, because oxide is always 2-. So that's always what an oxidizing agent would do. Something like that. I don't know if that's helpful or not, but that is, you can think about it in terms of oxygen.
Did you get 4?
4?
Yeah.
Because we assign the charges, or we assign the oxidation states based on that list of like priorities, and oxygen comes first. So when you see oxygen in a compound of carbon, hydrogen, and oxygen, you give the oxygen 2- first, and then carbon, you calculate the carbon from that. So you've got 2 2- oxygens, carbon's 4+ then, to balance it out to 0. The reason for that is that carbon can have more variable charge, variable oxidation states than oxygen. Oxygen's usually either 0 or 2-, with the exception of peroxide. Whereas carbon can be any number of things depending on what compound it's in. So usually calculate the carbon later, after the oxygen. Okay. All right, what else are we going to talk about?
Can you do a problem like
find the mass like in this? Because in the
I don't know. No, I don't know what you're talking
homework
about.
has like a question
Sorry.
where it's like this amount of ore is in here.
Oh yeah, okay. I remember that one. So let's pull out one of those. I think that's a chapter 2 or chapter 1 maybe. That was a tough question. Maybe it's chapter 2. Okay, yeah, I think it's something like this. Let's do like this one. All right, so gold alloyed with other metals. How many gold atoms in a 0.255 ounce 18 karat gold bracelet if 18 karat gold is 75% gold by mass? Something like that? Yeah. But first, this is ultimately going to be a mole type question because we got to figure out the number of atoms, and we know the number of atoms per mole. And then we've got a mass, it's in ounces, so we have to get that to grams. But the other part of this is that we don't use this whole quantity and convert that all to grams because we've only got 75% gold. So we first have to take that percentage of that and then do the conversions. So 0.75 times 0.255 ounces is 0.191 ounces. So that's how much is actually not silver, but gold is actually gold. And then we can do the conversion from there. Like how many grams are in an ounce? Anybody know? Do I have that information? Is that in there?
Well, it's given here for a pint.
Oh, that's liquid. That's different. Do you have mass measurements in there? Yeah. We can probably look at the internet.
28.349.
All right, that sounds right. 28.4 grams per ounce. And then we want grams per mole. So that is 197. Yeah. 197 grams per mole for gold. And then we want the number of atoms in 1 mole, which is 6.02 times 10 to the 23rd. So we solve that out. 0.191 times 28.4 divided by 197 times 6.02. So that's 0.166 times 10 to the 23rd, or 1.66 times 10 to the 22.
So like on the homework
Mm-hmm.
for chapter 1, it's number 8.
The mastering chemistry homework? Yeah. Okay.
It gives you a radius. It wants you to find the volume.
Mm-hmm.
It's almost like the same. How do I kept getting like a different one.
This one? Yeah, this is kind of the one you were originally asking about, right? Yeah. This is a tough question. So you have to find you have a bunch of different percentages that keep like compounding on each other. So you have to multiply by every percent because every percent gives you a little bit lower. So you'd multiply by 0.866, then 0.685, then 0.925 of whatever you get. But to first find that lead sphere, we have to figure out the volume of the sphere, and we need the density of lead to figure out how much mass before we can add all that stuff together. So if we have a 6.50 centimeter radius, the volume is 4/3 pi r cubed. You don't have to remember that, by the way. That kind of stuff won't be on the exam. Which is 4/3 times pi times 6.50, which is 1.33 all cubed. And like that, 1146. So we'll say 1.15 times 10 to the 3. And that's cubic centimeters. So that's the volume of the sphere. Then we need to know the density of lead to figure out the mass of that sphere. It's not in the problem, I don't think, is it? Anybody look it up?
I have 11.34 kilograms.
Sounds good. All right, so the mass of lead then is going to be 1.15 times 10 to the 3 cubic centimeters times the density, which is 11 point, what did I say? 3 grams of lead in 1 cubic centimeter. Okay, that's going to be 1.30 times 10 to the 5th. Wait, 4th, sorry. So that's the mass of lead that we need for the sphere. So now you have to say, whoops, there. So now we have to say, all right, if we're starting with this galena, or galena, and the galena comes from the ore, how much ore do we need to ultimately get to this much lead? So we take the ore, we take 68.5% of it, then we take 86.6% of that, then we take 92.5% of that, and that last number should be what all that is, should come out to this. So that means the mass of ore, which we don't know, times 0.685 and
0.866,
866
and then 0.9.
and 925. All of that should end up being 1.30 times 10 to the fourth grams.
I'm gonna get like one of those like in the test.
I mean, it's certainly fair game. Yeah. It's a conversion type question. I don't think you'll get something exactly like this, obviously, because we're just doing it. But, you know, yeah, being able to think about these things in that way, sure. So 13,000 divided by 0.925 and 0.866 and 0.685.
2.36 times 10 to the fourth.
Yeah. So we got a little bit of a rounding error, but close enough. Oh, all right, we're out of time. Let's